Equilibrium in chemistry refers to a balance between the two opposite directions in a reversible reaction, right? So, for example, if you want to talk about a process like um, water as a liquid becoming water as a gas, just vaporization, this is a reversible process because if you have a sample of water in a closed container, let's just say it's like a water tank um, or a beaker with a lid on it, doesn't really matter. As soon as we get some water molecules in the gas state, those water molecules are going to be bouncing around and bumping into each other and going back to the liquid state as some of those hydrogen bonds are able to take over and reform the liquid. So we have initially a whole bunch of vaporization, but after a while, some of that vapor is going to come right back to the liquid state, right? So these guys are going to bounce into each other and recondense to form liquid. And at first, obviously, when you first put that lid on, vaporization is the only thing that's really going to be able to happen. And so your forward arrow is going to be much, much larger. And then within a couple seconds, you start to get a little bit of the reverse reaction, but then it gets more and more and more, and eventually the rate of the forward reaction is equal to the rate of the reverse reaction. And so this is what we call chemical equilibrium, when the forward and the reverse are happening at the same rate. Now, it does not mean that the amounts of liquid water and water vapor are going to be the same, right? Almost certainly, assuming that you've got, this container about half filled with liquid water, there's nowhere near as many water vapor molecules floating around inside of here. Okay, so now let's take a look at a chemical reaction, or at least a hypothetical one, where essentially this diatomic hypothetical A2 molecule is going to decompose into two A atoms, right? So here the little red represents a diatomic molecule of A2, and then the little purple is just it once it's split up into two individual atoms. So you can see the 2A arrow, which means it's a reversible reaction. Well, at time equals 0, we have, it looks like 5 of our little A2 molecules. Let's assume this is about a 10-liter container, and that each of those molecules represents a mole rather than just a single molecule, so that we can use some numbers to express concentration. So at time equals 0, when I first seal the container with the gas inside of it, I've got 5 moles of A2 in 10 liters, so 5 over 10, so that would be 0.5, right? So 0.5 molar A2, and of course 0 of the A, because none of it is formed yet. The forward reaction hasn't had a chance to get going. And then after, let's say, 10 seconds, it looks like I have decreased the amount of A2 molecules, so some of that forward reaction has happened. So now I'm down to 3 moles in 10 liters, or 0.3 molar. And I've gone up to, it looks like 4 moles of A atoms in 10 liters, so 0.4 molar, right? And notice we can talk about concentration here because these are gases, right? So gases or aqueous substances. All right, so at 20 seconds, so another 10 seconds has passed, and it looks like we're down to just 2 moles of our A2 in 10 liters, so 0.2 molar. And we've jumped up to 1, 2, 3, 4, 5, 6, or 0.6 molar of the A atoms. And then after another 10 seconds, it looks like we're still at the same concentration. So 0.2 molar of the A2 and 0.6 molar of the A. And so what does this mean? Well, it doesn't mean the reaction has stopped, right? It's a reversible reaction. So somewhere in between 20 and 30 seconds, we still had the moles of A2 decomposing to form A atoms, but we also had A atoms coming back together to form A2 molecules. So the reaction is happening in both directions at an equal rate. So our concentrations stayed the same from 20 seconds to 30 seconds. And once we've established that, we are at equilibrium. It doesn't mean that the numbers are the same, and of course they're not, right? The A2 is smaller, but it just means that they're going to remain constant because we've reached equilibrium. Okay, so now if we wanted to look at this on a graph, we have concentration versus time here. So concentration of A2, concentration of A, and I guess I could color code them, but we'll continue to make the A2 red. So if I start my little line of A2, we'll make A purple. So if I start my little, well, let's start with the easiest one. The starting concentration of A at time equals 0 is, of course, 0. So we should get a nice dot right there at 0 molar. And then my concentration of A2 starts out, it looks like at 0.5 molar. So it's going to be right here at time equals 0. And then at 10 seconds, the A2 goes down to 0.3. So it's going to be right in here. And the A goes up to 0.4. So they've already kind of crossed each other. And then at time equals 20 seconds, we've got A2 has gone down to 0.2. So there's our little red dot. Okay. And then A has gone up to 0.6. And then if I just continue there at time equals 30 seconds, we're still at 0.6 for the A, and we're still at 0.2 for the A2. And presumably, even though we don't have the data for it, we can probably assume, unless this thing gets disturbed, that they're just going to kind of hang out there. And so if I try to draw a line here through this, it looks like we have something like this. All right, so what we have here is once we get to about 20 seconds, from 20 seconds on, so from this point on, we have reached chemical equilibrium. The concentrations of each substance don't change. So sometimes you'll get a graph like this where the products go beyond the reactants. Sometimes you'll get a case where the forward reaction isn't so favored, and so you'll get a really low concentration. But the point is, if these two lines are flat, then we know that we've reached equilibrium.